Okay, so today we're going to be integrating this function, and the method that we use is called a change of variable. And the way that we do this change of variable is that we let x equal a sine theta. Now we differentiate this and we get dx by d theta is equal to a times cos theta, which is the derivative of sine theta. And we do one more step and bring up the d theta over onto this side. The reason we do this is because we want to get a value of dx in terms of d theta, so that we can substitute it back in for dx here. Okay, so now we can go ahead and substitute all our values of x and dx into the original integral. So we have our integral is equal to the integral from, and I'll just leave the limits of integration for a moment, a squared minus a squared sine squared theta, and I'll just write to the power 1/2, which is the same as the square root, times, now dx is equal to a cosine theta d theta. Right. Now for our limits of integration, we need to change them to match this new variable that we've introduced. So when x is equal to a, we have that a equals to a sine theta, and so 1 equals to sine theta, and therefore theta is pi over 2. Similarly, when we have x equal to minus a, we get minus a equals to a sine theta, so minus 1 equals to sine theta, and therefore theta is minus pi on 2. So now when x was equal to a, we had pi on 2, and when x was equal to minus a, we had minus pi on 2. Okay, so now we can go ahead and simplify this a little more. So this is a squared into 1 minus sine squared theta, that's the square root of that, times a cosine theta d theta. Now it's important to remember the trigonometric identity. This tells us that cos squared theta is 1 minus sine squared theta. Now we can substitute that into here. We get a squared cos squared theta. We take the square root of that. We multiply that by a cos theta d theta. Okay, now when we simplify this, we'll get a squared cos squared theta d theta. Okay, now this is something that you will know how to integrate from your 3-unit mathematics. So first we can take out a squared because it's just a constant, and we'll need to substitute in, well, not substitute, but we need to find a nicer way of writing cos squared theta. So if you remember back to your double angle formulas, remember that cos 2 theta is 2 cos squared theta minus 1, and rearranging for cos squared theta, you get a half into 1 plus cos 2 theta. Okay, now we can substitute that in for cos squared theta. So we have a half 1 plus cos 2 theta d theta. Yep. Okay, now again a half is just a constant, so we can take that outside the integral. And now we can integrate this. This is fairly simple to integrate now. So the integral of 1 is just theta. The integral of cos 2 theta is sine 2 theta divided by the inside derivative here, which is 2. So we got this 2 on the bottom from the derivative of 2 theta, which is 2. Right? And this is evaluated between pi over 2 and minus pi over 2. Right? Okay. So continuing, we get a squared over 2 is equal to, substituting the top limit first. So we get pi on 2 plus sine of 2 times pi on 2, which is just pi, over 2, take away. Now we substitute in the bottom limit. We get minus pi on 2 plus sine of 2 times minus pi on 2, which is just minus pi, divided by 2. Okay, now we can simplify this down. Now sine of pi is 0. In fact, sine of any integer multiple of pi is 0. So this is a 0 here. We have minus, open brackets, minus pi on 2, plus this is an integer multiple of pi. So sine of the integer multiple of pi is 0 as well. So we get 0 here as well. We get a squared over 2 into pi on 2 plus, because we have minus minus, so we get plus pi on 2, which is equal to a squared times pi over 2. And that is your final answer. So therefore, the integral between minus a and a of a squared minus x squared, taking the square root, dx, is equal to a squared pi over 2. Now this is quite a lengthy integral here, because we have to do a couple of things. We have to first make this substitution, and then we have to remember some of our trig formulas. But there is a nice neat way that we can compute this integral without actually having to do any integration. And this is how you do it. So if you have this integral, I'll just rewrite it. This represents the area underneath a curve, because that is what an integral does. Now the curve here is y equals a squared minus x squared, taking the square root. Now you might recognize this as a semicircle, because if you square both sides and you rearrange it, you can get x squared plus y squared is equal to a squared. Okay, so now that we've recognized this as the top half of a circle, it has a radius of a, so here is minus a, here is a, here is a, and this is the y-axis, that is the x-axis. So this represents the area underneath this curve. So this represents this area. Now we know that the area of a circle is pi r squared, so the area of half of a circle would be 1/2 pi r squared. But here, the value of r is a, so we have 1/2 pi times a squared, which is the same value that we got before. And so therefore, this integral here is equal to 1/2 pi a squared. And that is a nice, neat way of finding the value of this integral without actually integrating it. Okay, thank you.